So I wanted a problem that talked about Raoult's law, especially since we had a quiz on it, but it wasn't really mentioned in the exam. It's an interesting concept. It makes you think a lot about the effects of pressure and intermolecular forces and how they work together, and includes some calculations, which is finding the vapor pressure. But I think it can also easily be added into the vapor question we already had on the exam, just by giving an actual or observed vapor pressure and saying, oh, can you compare it to the one that you calculated? And it would just add a little bit more to that question. This is the question that I made. It is a solution consisting of 30.87 grams of solvent Andrastia, 80.43 grams per mole, and 70.42 grams of solvent Callisto, which the molar mass is 83.38 grams per mole, is observed at a temperature of 20 degrees Celsius. At this temperature, the vapor pressure was 90.43. The vapor pressure of Andrastia is 47.37 torr at 20 degrees Celsius, which is the same, and the vapor pressure of Callisto is 120.91 torr at the same temperature. Is the behavior of this solution ideal, or does it have a deviation from Raoult's law? If it deviates, is this deviation negative or positive? And compare the intermolecular forces of the observed solution to the ideal solution. So from now on in the calculations, I will refer to Andrastia as A and Callisto as C. So the moles of A, you have to find the moles, of course, first before you can do anything. So the moles of A, we take the 30.87 grams that we were told we have, and we are given the molar mass as well. So we put the grams on the bottom so that they cancel out. So we have 0.3838 moles of A. And for C, we do the same thing using the grams we're given and the molar mass we're given to find 0.8454 moles of C. And then, for vapor pressure, we're going to use those moles we just found to find the mole fractions for C and A. The mole fraction of A will be the moles of A over the moles of A plus the moles of C, which gives us 0.3122. And it doesn't have units because mole fractions don't have units because it all cancels out. And the mole fraction for C is moles of C over moles of C plus moles of A, which gives us 0.6878. Then we'll find the vapor pressure so that we can compare it to the observed vapor pressure to see if it's a negative or positive deviation or if it behaves ideally. So to find vapor pressure, you use the mole fraction of A times the pressure of A plus the mole fraction of C times the pressure of C. And if we input all of our values using the pressures that we are told in the question, and we don't really have to change anything around because everything in this problem is at 20 degrees Celsius, we get 98.57 torr. Since the observed is 90.43 torr and the expected is 98.57 torr, and expected is like what you would expect the solution to do given your calculations, this means that it is a negative deviation, meaning that the actual one you saw, like in the experiment, was less than what you expected, had less pressure than you expected. This means that the intermolecular forces in the experiment or the observed solution are greater than in the intermolecular forces for the ideal solution. Because as the intermolecular forces weaken, then more of the solution can vaporize, which gives it a higher vapor pressure. And because it has a lower vapor pressure than we expected, then that means that the intermolecular forces were stronger because it didn't let as much vaporize.